Hi everybody. Hopefully you're kind of on to section 10.7 right now. But looking at this, we have these things called chord segments, which basically we have a chord like AC. AB would be an example of a chord segment because it's basically a segment of a chord, and BC would be a chord segment. But whenever you have chords that intersect at the interior of the circle, those chord segments, the product of AB times BC is equal to EB times BD. So that's a pretty straightforward one. But again, what's really important is where do these chords intersect? If it's on the inside, then that is a true statement. Those small chord segments, the product of those are equal to one another. Then we have these things called secant segments. So a secant segment is we have a secant, again, it intersects the line at exactly 2 points. But notice we've got these little segments. So AB and BC and AD and DE are examples of secant segments. Now, external secant segments are the ones outside the circle. So AB and AD are the only external secant segments in that drawing right there. Because again, they're outside the circle. So right here, so again, what I told you, it's important to know where do these intersect to figure out what's true. Notice these secants intersect outside the circle, external to the circle. What happens there is we then you have the external secant segment times the whole secant segment. So you have AB times AC is equal to AE times AD. So that is something that we're going to apply. But again, this meets outside the circle. So here in this example where we have this, so notice we have an external secant segment. So I know that X times this whole thing, our RU here, which is X plus 9, is equal to 4 times 4 plus this part, which is 9, the whole thing. So I now have this x squared plus 9x equals 36. And it's a quadratic, so we think, hey, I'm going to set it equal to 0 and hope that it factors, which I believe this one does. So again, you think, what multiplies to be negative 36 that adds up to be 9? And you will end up with x plus 12 times x minus 3 equals 0 when you factor. You can go through and do your a times c and break that all down. So again, we have something times something equals 0. One of those somethings has to be 0. So you set x plus 12 equal to 0 and solve. Well, one answer you get is negative 12, which doesn't make very much sense when we're talking about length. So our only answer here is x equals 3. This one is known as an extraneous solution because we can't have a length measure that's negative. So there's one example there. And then we also have one more situation where these do meet externally. However, notice this is also the point of tangency, this little secant segment here. So what happens then is you take this length of your secant segment and you square it. That is equal to this external secant segment times the whole thing, the product of that. So this length squared equals the short length times the whole length. So here's an example that we have. So our external secant segment that is tangent, so we're going to have 10 squared equals external secant segment, which is x, times the whole thing, which is x plus 4. So you're going to get 2x plus 4. So then we go through, and again, we're going to be super excited, I hope, because it's a quadratic and we love them. So again, when you do this, the first thing I would do is keep your squared term positive. I just think it's easier. So we set it equal to 0 and have 2x squared plus 4x minus 100. And me personally, I see that there's a GCF of 2. I would factor that out. We're left with x squared plus 4x minus 50. This is still equal to 0. Are there any factors of negative 50 that add up to be 4? And hopefully you've come up with the fact that it is not factorable. So me, again, I notice that b's even. So what I'm first going to do is divide everything by 2. Let's get that 2 out of there. So come on down here, and we now have 0 equals x squared plus 4x minus 50. And I'm going to solve this by completing the square to give you all a little review of that. And some people really like to have the 0 on the other side, so I'm going to appease those people. Oops. Now, when you're solving by completing the square, First, I would move the constant over to the other side. So we have x squared plus 4x equals 50. Notice I left a little space because my goal here when I complete the square is to create a perfect square trinomial. Take half of your b, which is 2, and square that. So we are now adding 2 squared to both sides. This now becomes x squared plus 4x plus 4, which is a perfect square trinomial. So it becomes x plus 2 squared equals 54. Oh, hold on, I'm coming back up here. You all probably already noticed this. This should be a 2x right here. I apologize. And that should be a 2x. That should be a 2x. That should be a 2x. So I really should have added half of b here, which is 1. 1 squared is just 1. So I'm adding 1 squared to both sides. Sorry about that. So that's 51. So now this is x plus 1, the quantity x plus 1 squared. Sorry about this messiness. Take the square root of both sides, and you get x plus 1 equals plus or minus square root of 51. So x is equal to -1 plus or minus square root of 51, which that's 3 times 17. You can't break it down, but you do have an extraneous solution. Your answer here is only going to be -1 plus square root of 51, which will approximately, in your calculator, it will give you -1 plus square root of 51 will approximately give you 6.14 if you are into approximating your answer for x. So I apologize for that little mistake. You guys probably noticed it well before I did. So hopefully this helps with this section. I know there's a lot with circles and we're flying through them, but circles are really cool, so I hope you're embracing them a bit, and I'll talk soon. Bye.